Hi, and welcome back. So, if you remember, we are doing a study about a model um, to control the mosquito population, and to be more specifically, the dengue mosquito. So, the dengue mosquito is a vector that can spread the dengue virus. So, um, this study proposed this method um, to control the dengue mosquito population. So also again, let me um, credit the authors. Um, I'm taking this from this book, Researches Applied in Math Modulation, from these authors, Aaron and Paulo Salsin and Sandro Senwick. Okay, so again is a analysis of the mosquito population model, and the method which is used. Um, I say that this is a method. Um, this is a model. So this is a model, and the method used to control the mosquito population is the feedback linearization. And again, let's just briefly do a revision of what we already have saw, and then we can continue describing the module. So the feedback linearization is a procedure that allows to transform the dynamic of a nonlinear system into a linear system by feeding back the nonlinear system. So right here we got this. We are still elaborating this model, which is a nonlinear system, and with in order to accomplish our goal, which is control the mosquito population, we introduce into the model a counter variable. So this variable um, allow us to transform this nonlinear model this nonlinear system into a linear system in which we can do the control. So we already has passed through this first introduction. So I introduced the variables of the system. So we got x1, x2, x3, x4, and okay, so this is also divided into phases. So we got the aquatic phase, we got the winged phase. So this is a problem not only of a system of equations itself, also is a problem with this context that we need to interpret in order to be able to elaborate a solution. Okay, so let's just revise this. On the aquatic phase, we got the variable x1, and this variable is representing the eggs, the larvae, and the puppies. Um, on the winged phase, we got the variable x2, which is represent the mated females. We got the variable x3, which is represent the fertilized females, and the variable x4, which represents the females. Sorry, the males. And as you can see, we are working with the base time. So is x1 of t, x2 of t. Okay, we also got other variables, which is the mortality rate uh, from each stage of development, from each stage of development of the mosquito. So for the first stage, which is eggs, larvae, pupas, we got mu1, which is a mortality rate. So each of these variables is a mortality rate for each stage of development of the mosquito. We also got the oviposition rate, represented by this variable. And this P represents the intrinsic oviposition rate. C is the capacity of the environment in terms of food and other needed for the mosquito development. We got gamma, which is how they move from the aquatic phase to the winged phase, and this is all this also are rates. We got R, which is represent females, and R minus 1 representing males. We got beta, again another rate, which is represent the mature females mating rate with males. Okay, so we already has started to write the systems of equations. We first wrote this x1 dot, which is the dynamic of x, or the rate of change of x. And as you can see, if x1 is of the first stage, which is the eggs, larvae, and pupas, to write this equation, we need to look at the variables which is relating this first stage. So the oviposition rate is related to this first stage. So the mosquito is directly related to this rate, and we are multiplying this rate to this variable x3, which is the fertilized females. This is the density of mosquitoes, which is fertilized females. So x3 is directly related to these oviposition rates, because if x3 is the fertilized females and its capacity to lay down eggs, this variable, this rate, is this capacity of lay down eggs, and this is why we are multiplying x3 by this rate, and we are doing a subtraction to gamma, and gamma is being also subtracted by mu1. So let's see, gamma is how this mosquito will move from the aquatic phase to the winged phase, and is a rate which is also directly related to the aquatic phase, so it's directly related to x1. And we a subtraction of this rate, gamma, from mu1, which is the mortality rate, and we multiply this subtraction of rates by x1, which is the aquatic phase. So how they will move from the first phase, which is the aquatic, to the winged. And mu1 is the mortality rate. So none of them will survive on this fourth stage. So we need to consider this when we are modulating this system and multiplying by x1, which is this first stage. Okay, and doing this interpretation, the authors were able to write this first equation. Okay, and it's a system of equations. So right here, we got 3 more equations. So now we need to see which of these rates, these variables, are related to x2, which is the winged phase, but is the density of individuals of the population of mosquito, which is mated females. So it's the females that they did not mate. Okay. So first, let's see all the variables and rates related to this second stage of development of the mosquito. Okay, we got x2 itself, and again, which is the density of individuals of the mosquito population, represented by the unmature females. Unfertilized, let me see, unmated females, the females that did not mate. They can be fertilized, but they did not mate. What else? We need to relate all the variables in rates. Mu2 is also related, is the mortality rate of this second stage. Now notice the oviposition rate is not related to this stage because this is for mated females, and if this female did not mate, so they don't have eggs to lay down, so this oviposition rate is not related to this second stage. Gamma is related because gamma is how the mosquito will move from the aquatic phase to the winged phase. So this rate is valid for all these stages because it's how the mosquito will move from this phase to this second phase. So gamma, and now R, because we are separating females from males. So R is related. What else? Immature females mating rate with males. This is a rate, and it's not for fertilized females, it's for immature females mating rate. So is a rate that relates the immature females, how they will mate with females. So beta is also related to this second stage. And if is still on beta, if is the immature females mating rate with females, we still need to consider how much of these individuals on the population it will survive after the mating. So we need to relate to mu2. Okay, and yeah, so now we need to, this description, we need to write another equation from this description. Okay, so first R, which is the quantity of females that made it from passing to the aquatic phase to the winged phase. So R n times gamma. We could write gamma times R. Gamma is the quantity of individuals of the population made it to pass from the aquatic phase to the winged phase, and R is the rate of females inside this rate, the gamma rate, because we have R minus 1, which is for males. And actually right here, we still need to consider X1 because some of the individuals that made it passing from the aquatic phase to the winged phase, we count them right here on this variable. They also represent the population of mosquito, the density of the population of mosquito, which is mated females. So we got the females that still did not mate, and we got the, well, eggs, larvae, and pupils, and then become mosquitoes, so the new ones. So X1 is also related to the unmated females because it's the ones that are becoming mosquitoes, and we got the ones that were already developed and the ones that still are in development, and we are starting to count them right here. So we multiply this this variable right here. So it's x1 times this rate, which is the quantity of these individuals that manage to pass from the aquatic to the winged, and minus, let's see, beta is the immature females mating rate with males. So it's how much of these individuals are mating, but it doesn't matter if they are mating because they are immature. And right here, we need to notice this. We got mated females, so it can be um, immature females that did not mated, uh, and we got fertilized females, so is mature females that they are fertilized. So we subtract this beta because it doesn't matter if they are mating because they are immature. And we also need to consider the mortality rate on this stage. So it doesn't matter if these females are mating because they are immature, and we need to consider um, the individuals that die. So mu2, which is the mortality rate. And we also consider this mu2 on both stages of development of the mosquito, because throughout the development in all stages we got this chance of some of these mosquitoes dying. And we multiply these rates, the sum of these rates, by x2, which is again the density of mosquitoes, of the population of mosquitoes, which is mated females. So from this density of mosquitoes, a population of mosquitoes, which is mated females, some of them can be immature females. So this is why we are multiplying this variable to beta, and beta summing to this rate of mortality. Okay. We got more two equations to write. So we got our system of equations, and we got our nonlinear system. And again, in order to transform this into a linear system, we will introduce a counter variable. Again, so this dot, it means the dynamic of the x, and is also the rate of change of x. Again, so let's just do a review of we cover on this video. X1 is a variable that is representing the eggs, the larvae, and pupils. So we got X1, and some of these individuals, after it pass from this stage of larvae, of pupils, that it becomes the mosquito. Some of them will mate, some of not, and the rate which represents this, how they mate, passing through this aquatic phase to the winged phase, is the gamma rate. So we multiply x1 by gamma, and some of this population that manage to pass through this aquatic to the winged. Some of them are males and some of them are females, and R is representing the females. Minus beta, which is immature females, the rate of immature females, mating rate, and we sum this to a rate of mortality. Consider in all stages that some of these individuals will die, and we multiply by x2, which is the density of mosquito population, which is mated females. And we are representing this density of mated females as the equation x2 dot. Okay, so for now it's all. I got a bit confused trying to explain this to you. And again, I will watch this video, and the parts that it don't comes out very well explained, I will try to explain again. And that's it. Thank you.